In this video, we will learn about the last section of the textbook of chapter 9, which is 9.5, the inference about the two population standard deviation. Now, in the last video, we talked about section 9.3 in the textbook, which was the inference about the two population mean, and they was independent sample. Remember, for the mean, there are two types, dependent and independent sample. Now, in this section, we will learn about the last one, which is the standard deviation, or sigma. So recall from the last chapter, we studied about the population proportion, then the mean, and the last one is the standard deviation. For the proportion, we use the z statistic, right? And for the mean, we use the t statistic. And for standard deviation, we use the chi-square. In this chapter, the last two parameter, the proportion and the mean, we also follow the same type of statistic. But for the last one, this one, standard deviation, we are not using the chi-square anymore, but we use something called the Fisher or the F distribution. Now, sigma 1 and sigma 2 here, sigma 1 square and sigma 2 square, they are the variant for the population 1 and 2. Remember, in this chapter, we talk about the two population. We're comparing two population. Therefore, you have 1 for the population 1 and 2 for the population 2. And again, S1 square and S2 square are sample variants. That's which mean this is the variance of the data we collect for the two populations. Now, they are taking the data from independent simple random samples for size N1 and N2. And the Fisher's or the F distribution follow this rule, which is the sample variance of the first population dividing the sample variant of the second population. And this one follows something called the F distribution, not T. T is for the mean, Z is for the proportion, and now F is for the standard deviation. The degree of freedom, there are two different degree of freedom. N1 minus 1 is the degree of freedom in the top or the numerator, right? S1, which is the population 1, so we have to take the N1 minus 1 from the sample size N1 for the top, and for the bottom we have to take the N2 because we are using the S2 at the bottom. So N2 minus 1 degrees of freedom is for the bottom. And you can see here, different type of degree of freedom will give you a different distribution. So the first objective is to test the hypothesis, the same type question. Now, before we do any testing, make sure that the samples are obtained using the simple random sampling. This is always true in this class. And the sample data are independent. So make sure that I have to give you something that I collected from independent sample. The populations from which the samples are drawn are normally distributed. So we want to be that normally distributed. It is not enough to have a large sample. Remember, from the last three sections, proportion and the mean, we need the sample to be at least 30 for both of them, right? But in this section, for the standard deviation, it is not enough to have just a large sample, but we also require the samples must be checked using a normal probability plot, no matter what the size of the sample. This is the different thing from the last three sections. Now, the notation we use for comparing to the two population standard deviation. Sigma 1 square is the variance for the population 1. We already knew that, right? Sigma 2, the variance for the population 2. S1 square, the sample variance for population 1. S2 square, the sample variance. This is a sample size, and this is also a sample size for population 2. Now, the step for conducting the hypothesis about the standard deviation, they are pretty much similar comparing to the last three sections. The first thing is you must always determine the null and alternative hypothesis. And in this case, the null hypothesis, the two standard deviation, they are always equal to each other, no matter which cases here, but they are always equal for the null hypothesis. Now, for the two-tail, the alternative hypothesis saying that the two standard deviations are not equal. The left tail, the first one is bigger than less than the second one, which means the error is pointing to the left for the left tail. Now, the first one is bigger than the second one, and we will have the right tail, or the error is pointing to the right. The level of significance alpha is always given to you, and this is based on the seriousness of making the type 1 error. After you have the null and alternative hypothesis, we have to calculate the test statistic. In this case, it's the Fisher or the F statistic, which is the ratio of the sample variance of the first one to the second one. After that, we will find the corresponding p-value using the FCDF. It's not TCDF, right? TCDF is for the T distribution. It's not T, and not chi-square. This is the FCDF function. And the comment for that is using the TI-83 or 84, you will have to put the lower bound, and then the upper bound, and then the degree of freedom in the numerator or of the first population, which is n-1 and 1-1, and the degree of the freedom in the denominator, or n2-1. This is from the bottom, this is from the top. And make sure that for the two-tailed test, we need to double the FCDF results, right? Remember, we also always have to multiply by 2 to get the p-value for the two-tail. Because two-tail, we are looking for the 2n here. So when we get the FCDF 1, you have to multiply by 2 because we are looking for the 2 area. So we double the value of FCDF. And then we're going to make the conclusion. Again, the same procedure. If the p-value is less than the significant level, then we reject the null hypothesis. The procedures just presented here in this way, they are not robust. But again, this is the one of the best way we can do in this class. And make sure that you have to meet the requirement before you can apply this F statistic here. Okay, so let's try the very first example. So we use the same example from the last video. So a researcher wanting to know whether the state quarters has a standard deviation weight that is less than the traditional quarter. So the state quarter here is the first population, and we are comparing that to the traditional quarter or the second population. And the key word here is the less than. So we want a standard deviation that is less than. So 1 is less than 2, or L1 is less than L2. Now we collect the data here, and you were told that's a normal probability plot indicating that the sample data is coming from the population that is normal, so you don't have to worry about that. And the alpha is 0.05 in this case. Now so that all requirements are met, we're just gonna find the null hypothesis first. So again, the null hypothesis saying that the two standard deviations, they are always equal to each other. And now we want to test whether the first one is less than the second one, or now the alternative is the first one less than the second one. Less than here, the arrow is pointing to the left, or we are going to have the left tail in this case. The level of significance is alpha equals 0.05. Now this is the sample variant of the first data. This is the sample variant of the second data. So you're gonna put this 18 value here to the TI 83, 84 and compute the variant or standard deviation first, because when you square that, you get a variant. So the standard deviation of this data from the calculator gives you, from the last section, is 0.0497, and add 2 is going to be equal around 0.0689. And in order to get the Fisher here, the Fisher statistic, S1 square, so take this number square, 7 square, over this one, 0.0689 square, and that should give you around 0.5203, and that is the Fisher. Remember, it is not done yet for the test statistic. You have to find a p-value. This is the critical step for the p-value. Now, the p-value, remember, we are using the F distribution, right? So for the p-value, you have to use the FCDF. And for this one, in this case, we know that this is the left tail, or you are looking for the left area, and you got something around the minus 0.5203, which is here. So around here, 0.5203. Oh, sorry, this is not correct. Let me rechart the picture here. So it shouldn't be symmetric. Rate this. Remember, for the chi-square and the F distribution, we don't get the symmetric curve like this, comparing to the last 3 sections, but you should get something similar to this here, right? It's just similar to the chi-square, so it's not symmetrical. So I guess the test statistic to be 0.5 something. So I should get something like that here. So 0. For example, 0. So this is not correct. 0.5203 maybe around here, and we are looking for the left tail, meaning that we are looking from this point and all the stuff to the left of that. Okay, now so the lower bound is the one that's all the way to the left, which is minus 10 to the 99. The right, the upper bound is this point, or 0.5203. Then the next one is what? The next common, the input of this one is the lower, the upper, the degree of freedom in the top and then also in the bottom. So for the top, which is the first population S1, we have N1 to be 18, right? 18 data. So this means that we have N1 minus 1 for the degree of freedom, or 18 minus 1, or 17. And then the next one we have 16 data. So the degree of freedom for the bottom is 16 minus 1, or 15. If you, this is the degree of freedom for the top. This is the top here, the degree of freedom for the bottom. So if you plug in this common in TI-8384, you should guess the p-value around 0.0982, and this one is bigger than 0.05, right? 0.09 is bigger than 0.05, which is the alpha. So because this is bigger than, we do not reject. So there is, if we do not reject, that means there is insufficient data or insufficient evidence to conclude that the standard deviation of the weight is less than for the stage quarter comparing to the traditional quarter as the 0.05 level of significance. Okay, that's the end of that example. Now there is one more example for this section. So again, we also want to test for the hypothesis regarding the two population standard deviation. Now read this example carefully. In a randomized experiment, 150 babies was randomly divided into a treatment group N1 75 and a control group N2 is 75. Now after the study, the treatment group has a mean serum retinol concentration of 49.72. So they are talking about a mean here, but pay attention to the next sentence. So they got the mean for the treatment group or the first group to be 49.79 microgram per deciliter. Now, with a standard deviation of 17.81 gram per dl. The control group also had a mean serum retinol concentration of 13.84 gram per dl with a standard deviation of 12.37 gram per dl. So they give you the mean of this one for the first group, and they give you also the standard deviation, the first group, and then they give you the mean of a second group, which is this, and the standard deviation for the second group is this. So they give you both parameters. But the question they ask you, you have to pay attention to this. Does the treatment group or the first group have a higher standard deviation? So they ask you, they are not asking you about a mean, but they ask you about the standard deviation. This is the question. So they ask you the standard deviation of the first group. Do they have the higher standard deviation comparing to the control group or the second group? So higher meaning that bigger than, or pointing to the right, or this is the right tail. So even though they give you the mean, but they are not asking you for the mean, you have to read the questions carefully. They ask you for the standard deviation. So we have to use the Fisher statistic for the two population standard deviation. and the level of significance is 0.05. So assume that this is normally distributed, so the requirement is good. Now the null hypothesis, remember, they are always equal. Okay. Now the alternative hypothesis is the one being in question, right? So the first one has a higher or bigger than the second one. So this is the one that we're testing against. So if in this case they already give you the standard deviation, the sample standard deviation of the first one is 17.81, and the sample standard deviation of the second group is 12.37. This is given, so you are good now. The F statistic is S1 square divided S2 square, or take this number 17.81 square divided by 12.37 square, and you should get around 2.073. Now this is the right tail, so let's draw the graph, the curve, and you should get a curve something like that here. And the right tail, we get the test statistic maybe 2.073 around here, and we are looking for the right tail, so we go from here and all the way to the right. So the p-value, again, the F statistic, you have to use FCDF, and the lower bound is 2.073. The upper bound is all the way to the right because this is the right tail, so we go all the way from 10 to the 99. And then the next one is the degree of freedom of the top. The top, we have 75, so the degree of freedom is 75 subtract 1. And also the bottom, also 75 samples, so the degree of freedom of the bottom is 75 minus 1. And using TID3 or 84, I get that around 0.000996, and this is much less than 0.05. If this one is less than the alpha, then we reject the null hypothesis, or this one is not correct, and we end up with the conclusion that the first group is having the higher standard deviation comparing to the second group. So that is the conclusion, or you can say that there is sufficient data or sufficient evidence to conclude that the treatment group has a higher, or the first group has a higher standard deviation for a serum retinol concentration than the control group at a level of significance of 0.05. So that is the end of this this section of standard deviation. So let's just summarize everything for this chapter. For the proportion, so we have the total of 4 sections, right? The first one is proportion, and then the next one is the mean, and then the last one is standard deviation, right? Now the proportion, remember, you have to use the z square, z statistic. The mean, there are 2 types. One is dependent, one is independent, right? And then the standard deviation is just one thing. Now for the dependent, you have to take the difference of the 2 sample size, the 2 sample data. So you always have to find the difference because they are dependent to each other. So you have to relate them to each other. For independent, you can keep them separately. In these cases, we are using the t statistic for the mean, and for the standard deviation for this one, we are using the f. This is not a chi-square anymore. This is the f. Okay. So there's total of one section. 2 here, so 3 with this one is 4. So we have a total of 4 sections in this chapter, and this is the end of chapter 9 in your textbook.